Okay, welcome. We're gonna continue on here. We've been talking chapter 2, and last time we got into really kind of dimensional analysis, conversions, conversion factors, and equalities. We kind of put all that together since it all really does go together. So when we have something that's an equality, remember that that is basically two values that are on different units, but they do represent really the same sort of quantity of whatever you're dealing with. So again, just a basic sort of equality like 12 inches equals 1 foot. That again represents, as we talked about, the same sort of distance, uh, but they are on different units. And regardless of what type of equality that you're dealing with, you could always write two conversion factors from any equality. And as we talked about, really conversion factors are pretty much just fractions. So to write those conversion factors, we essentially just put one of the units up on top, like in this case, 12 inches, and the other unit on the bottom, like 1 foot. Or we could have a conversion factor where we have 1 foot up on top and 12 inches on the bottom. So these again are two conversion factors that you could use in a problem. As we also talked about, you should probably never use both of them together, otherwise they undo each other. So you should only choose obviously the one that you need to use. We talked about how to set this stuff up, which is dimensional analysis. And when we set things up using dimensional analysis, that is the way that we set up work to basically show the units canceling out. We use conversion factors in this. And really, as we talked about a lot last time, the way that we set those up, it sort of minimizes, in a sense, hopefully some errors that may be made in terms of math. The idea of that is if we have a certain unit that we want to get rid of, even if it's not written as a fraction, we could think of it like a fraction. And remember, when you're doing dimensional analysis, it's all about opposites cancel. So if you want to get rid of a particular unit that you no longer need, you need to put that same unit in the opposite location. So for example, if we had a conversion factor that had unit A in it, we would need to go in the opposite location to get rid of that. And unit B, for example, might be what we're looking for. What we do mathematically when we set it up like this, as we talked about, is anything that is up on top does get multiplied, and anything on the bottom pretty much gets divided. Now, because opposites sort of cancel, all you have to remember when you're doing these things is just put things in opposite locations. Because when we divide essentially unit A by unit A, it becomes 1 and essentially cancels each other out in this particular case. So if we had like 42.5 inches and we want to know how many feet that was, if we're looking for feet, again, we could think of this like a fraction. If it helps you to put it over one, do it so you can see the top and the bottom. You don't necessarily have to do it that way. You could just leave it at 42.5. But again, by seeing that inches are on top, I need to get rid of them. It makes picking the conversion factor pretty simple because everything's written sort of in this top and bottom sort of location. And I know for sure it's got to be that one there on the right. That's going to cancel those. Again, we're going to multiply what we got here. We're going to divide what we got here. And in this particular case, not much to multiply up there on top, but we'll take, if I clear my calculator, 42.5 divided by 12. And that's going to give me on my calculator here 3.541666667. And clearly, the only units left there on top are feet. We obviously never want to give an answer with that many digits, so we want to also think about significant figures here. And the reason when we set things up in dimensional analysis that we only have to think about significant figures is the only operations that you do in dimensional analysis is multiply and divide, which means that is what you should be looking at. Remember that when we use conversion factors, for the most part, a lot of them are considered exact numbers. And the idea with exact numbers is they could have an unlimited number of significant figures. So when we come across something that's considered an exact number, we do not worry about it in terms of the answer and how many significant figures our answer should have. So the only time we really, in a lot of cases, have to worry about sort of a conversion factor is if we cross over from metric to English type conversions. But if you say sort of English to English conversions or metric to metric conversions, they will essentially be an exact number. You don't have to worry about it. The one sort of crossover that is considered, again, an exact number is the one that we saw as well. 1 inch is 2.54 centimeters. So although that is a crossover from, say, metric to English units, that is still considered an exact number, so you don't have to worry about it. So when we look at this, this is considered exact, so we don't need to worry about it. That means a lot of times, this is oftentimes where you're going to be looking for significant figures, but not always the place. And that has 3 significant figures, which means we should come to here, and this should come down to 3.54 feet. Again, a reminder that your calculator does not always give you, obviously, the answer to the correct number of significant figures. If you have more conversions that you need to do, you just kind of keep going down in that pattern of top, bottom, and kind of do that. As we also talked about, typically speaking, if you're looking to solve for one unit by itself, that unit usually ends up on top by itself. It is possible to have 2 units that you need to convert at the same time. And again, keeping things sort of on top and bottom allows you to sort of do the math correctly. And as we also talked about last time, sometimes just taking a more dimensional analysis approach to problems and thinking about units can allow you to bypass perhaps thinking about a formula or rearranging a formula. I'm not sure if you're, should be dividing or multiplying. So it kind of takes the guesswork out of the math part of it if you kind of set it up this way. Any questions on any of that stuff there? Okay. Obviously, if we did come across, though, a conversion that we needed to use between metric and English, we would look at, in most cases, the number that is a real number, if you will, rather than the one of that kind of conversion factor. So usually there's like a 1 and then some other number. So we would look at, obviously, the non-1 number to think about significant figures. Other places where we do want to look at significant figures, where we do use conversion factors, as we talked about before, is sometimes in problems you are given some information that's really not a true conversion, but specific for that problem. Like, for example, I think maybe we did how fast you were driving miles per hour or something like that. Those type of values that are given to you, you do typically need to look at the significant figures in those numbers when you're kind of doing the calculation. Any questions on that there? All right, so let's take a look at. All right, we'll actually skip this one. We did one kind of similar a second ago. I think we're going to go to, let's do this one. You're stranded 125 miles away from home. You decide, nice day, let's go for a walk. You walk 55 feet per minute. How many days will you be walking? Hopefully it's nice all those days. Okay. All right, so some equalities that might be helpful for you. So set it up, dimensional analysis, figure out how many days it's going to take you to get home. So let's take a look and see. So kind of a similar situation to one we saw a second ago. Here we have a distance that's in miles, and we have a rate, which is basically a distance over time. And again, that rate is what's going to allow us to go from, in this case, distance to time, since we are looking for days, which is a unit of time. We have the same situation as we talked about earlier. My distance here is in miles, but my distance here is in feet. So the way it sits there, they are not usable together unless you do a conversion. And again, as I mentioned before, it does not matter. You could either take the miles to feet or the feet to miles. I am going to take the miles to feet here and then just use this as a conversion factor. Obviously, that was given to us right there in the problem as a conversion factor. And I don't know what it says on your handout, but hopefully it says 55.0, I hope. So that's what we see here. So I'm going to use my miles here to feet equality and conversion factors to do that. So I'm going to start with that, 125 miles. That is technically on top, even though I'm not writing it as a fraction. So again, a reminder, those miles are up on top, right? So when you start with just one number by itself, it's basically on top. And we want to go opposite. So again, to cancel, we want to get rid of miles. That has to go on the bottom. My 5,280 feet need to go on top. And the miles here will cancel. That's going to give me a whopping 660,000 feet. Definitely gonna get your steps in today, I suppose. Yes. So now that I have it in feet, I am good to go with my conversion factor, which can be used as 55 feet per minute. Or on top, you could do a minute is 55 feet. Again, you could use it as a conversion factor either way, whichever way you're going to need to do it. I'm going to continue on here with my number there, 660,000, a couple more zeros, feet. Once again, not written as a fraction, but the feet are on top, which is really important because now it should make my decision pretty simple. I need the feet in the opposite location, which is on the bottom. That move right there is going to allow us to go from distance to time, basically here. That's going to give us 55 feet per minute. Feet on top and feet on the bottom will cancel. If I laid up the calculation right at this point, I am in units of minutes, which is good because we're at least in time, but we do want to get to days, right? So again, there's multiple ways you could get there, but we'll just go step by step. So again, minutes to hours in this case is what we're going to do next. Minutes are on top, so that means 60 minutes should go on the bottom. 1 hour should go on top. Minutes will cancel. And if I stopped right at this point, the units I am left with is hours, which is on top. Getting close to what I need. Hours now to days, right? Will get us there. And again, we talked about only 24 hours, right, in a day. So the nice thing again about setting up like this, there should be no misunderstanding. Hours are clearly up on top, right? So again, to get rid of them, we need to put the hours on the bottom opposite location. And 1 day up on top. Hours will cancel, going to leave us only days left, which is good. Once again, we are multiplying whatever's on top, however much we got, and we're dividing by what's on the bottom. Now, a reminder here, you want to be careful when you punch this in. There's really not much to multiply up on top since they're all basically ones, right? These are all basically ones up on top. We want to divide by the bottom, which is 55. After you do that, hit the equals. Yeah. Then you want to divide by 60. After you do that, hit your equals button. And then you want to divide by 24, hit your equals button. And you will get the right answer, hopefully. Again, if you try to punch all that in at once and you are not very careful, you will get the wrong answer. Yeah. So if you want the right answer, do it like that, and you'll probably be in good shape. Let's talk about a couple things like sig figs. I don't have to worry about this, right? I don't have to worry about this. Should I worry about this? I should. And this has 3 significant figures. Should I worry about this number? I should, but I should not worry about that number there. I should actually worry more so back this way, yes? And that number really had 3 significant figures, right? Which means even though I didn't write it with 3 significant figures, this number here should technically still have 3 significant figures, which means down here, technically, that number should have 3 significant figures, which means my answer should technically be 3 significant figures, yeah? In 8.33 days. That's a long walk. Hopefully, no stopping, I suppose. First off, any questions on that? Can't tell you how many people will do this problem or a problem like it and end up multiplying the 60 and the 24 when they should be dividing. So again, setting it up like this where you can clearly see top and bottom, remembering top you multiply, bottom you divide, you will hopefully do the right thing Again, if you kind of do not set it up like that, you will probably not get the right answer. And you should set it up obviously like that. It helps with the math, and you're supposed to show your work that way as well. Question on conversions, dimensional. Okay, any questions again on dimensional analysis, conversions? Again, you need to show your work that way. And as we talked about, it's probably a great idea to, when possible, just take a dimensional analysis approach. Again, it really does sort of simplify everything, simplify the sort of equation, the rearranging, and it can be very helpful. All right, now to finish up the last part here of this chapter. Hopefully, maybe, there it is. All right, the last thing we're going to talk about is density. And the density of an object is basically a property that determines, for example, whether or not an object will sink or float, say, in water. So, for example, or any substance really, if a substance is more dense than water, then it will sink. And if it is less dense than water, it will actually float. The density of liquid water is an important number to know because sometimes you do need that. So, and for the most part, you can use it as 1 gram per milliliter. So if you ever find yourself in a problem where technically you need the density of water, that is basically the number that you should use. By the way, just so you know, density does change with temperature. So if it happens to be a specific temperature, it can change. But I would say 99 times out of 100, if you're doing a problem, you need a density of water, that's probably the number you should lay up for liquid water. When we look at these things here, we can see that water there is 1 gram per milliliter. We have ice cubes, right, which is actually water as well. So ice, which is water in the solid state, is actually less dense than liquid water. And that's an unusual property for a substance. In most cases, things in their solid state is more dense than their liquid state, right? They could get in there really tight. The difference with water is when water tries to freeze, or when water does freeze, not just tries, because it doesn't have as much energy, and water molecules are basically held together through what are known as hydrogen bonding. When a bunch of water molecules come in to basically freeze, it creates a lot of really open space between the different water molecules, kind of swells it, if you will. And basically what that does, it actually lowers the density of ice. And that's, again, a very unusual sort of property. Usually it's the opposite. You're really more dense a lot of times in your solid state than in your sort of liquid state. So you see there some pieces of aluminum and lead are more dense than liquid water, so it is floating. The formula for density is D is equal to M over V. That is mass over volume. As I mentioned a second ago, typical units of density are grams per milliliter, are grams per cubic centimeter. These are the typical units for solids and liquids. If you're dealing with gases, which we really don't at all in this class, but sometimes you might come across it, the density of gases are typically given in grams per liter is typically what they're given in. But these are going to be your big 2 units for density here, grams per milliliter or grams per cubic centimeter. A reminder that 1 milliliter is equal to 1 cubic centimeter, right? It is a sort of 1-to-1 conversion. How do you get a cubic centimeter? As we talked about when we were talking about volume, if you have the length times the width times the height, and you measure each of those, say, in centimeters, and you multiply them together, you get cubic centimeters, which is a volume. Each of those individual measurements are actually length measurements, but when you have something like, say, a solid wooden cube or something like that, and you take those measurements and you multiply them together, you get cubic centimeters, which again is a volume. Clearly, milliliters you could get very simply by filling something in a graduated cylinder, for example, and taking a volume reading is one way that you could do that. Now, this equation is something that you should know how to rearrange, and you should know it might not be provided for you, probably not. So volume in this case would be mass divided by density, and we get that basically by multiplying volume to both sides and then dividing by density to both sides. Those cancel, and we end up with what we got on the bottom. Now, if you want the mass is equal to volume times the density. And those are kind of three ways you could rearrange this equation. Some people like to remember the DMV triangle because everybody loves the DMV, right? And density is mass over volume. Volume is mass over density, and mass is volume times density. So you remember the DMV triangle, and you could rearrange that pretty easily in this case. Any questions on that there? Now, when we have things that have a very high density, they typically are packed together pretty tight to one another. When we have things that are lower in density, they're not as packed in to one another. By the way, if I had different volumes of liquids that had different densities, they would typically separate out by layers, basically, right? So you would have different layers that would occur if you put some solutions of different densities together. Obviously, the bottom layer would be more dense. Obviously, the top layer there would be less dense. And if you put something in it that just kind of floats right about there, that means that whatever that dot is more dense than whatever's above it in terms of layers, and it is less dense, right, than anything below it as well, right? So it just kind of suspend itself sort of in that layer. Right. So as I mentioned before, typical units there, grams per cubic centimeters, grams per milliliters are grams per liter, right? Same idea if you take a bucket of water and you take a Diet Coke can and a regular Coke, right? And you put them in there, will they both sink? Will they both float? Will they do one of each? It's a good party trick. I know Super Bowl's yesterday, but it's a good party trick anyways, right? So actually one will sink, one will float. Which one was going to sink, you think? The regular Coke. It has a lot of sugar in it, yeah, making it more dense. Diet Coke's got artificial sweetener, not so much sugar, right? So it actually is less dense. So the Diet Coke would actually float, and the regular Coke would actually sink in that case because of the sugar. Here's some density of some common objects. As I mentioned before, water is usually the one that we look at and use at 4 degrees Celsius, which is actually the maximum density that occurs. That's also why, for example, water freezes from the bottom up or the top down, like in a lake or a body of water like that. It freezes from the top down, right? Otherwise, the fish are in trouble, right? If it freezes from the bottom up. And that's because what ends up happening is your warmer water, like your 4-degree water, sinks because it's more dense. Your cooler water actually goes to the top where it actually freezes, right? And usually sometimes it doesn't freeze so good, which is why they tell you not to walk on it, right? Because it will crack and you'll be in very cold water down there, right? And stuff like that. So that's why fish is right and everybody's okay when it freezes, right? Because it does freeze from the top down, not the bottom up. It has to do with density of the different water sort of temperature. All right. Now, as I mentioned, there's two common ways to sort of get volume, especially when you're dealing with density. So as I just mentioned before, you can do some length measurements. You clearly could just put a liquid in a graduated cylinder, right? Read the meniscus, very badly drawn meniscus there, and you can take a volume reading. The other really common way that we get the volume of an object is volume by displacement. And the idea of volume by displacement is this. You take a certain amount of a liquid like water and you put it into, say, a graduated cylinder, and you take an initial reading of that liquid. You take a solid object such as this, and you basically put it into that graduated cylinder that has the same water in it. And what's going to happen when you do that is the water level will go up or down. Will go up, yeah? So, and basically what will happen in this particular case is the object will displace a volume that's equal to itself, its own volume, basically. So we can very simply in this thing, which is a very common density sort of lab, if you take the difference in the final volume versus the initial volume, that will give you the volume of the object that you put in there. So the volume of the object is typically the final volume minus the initial volume. And you'll be able to very easily, like a rubber stopper, or whatever it may be, a solid, whatever you want to dump in there. You can very easily figure out the volume. And clearly, that's easy to do. And you could just take the solid to a balance and put it up there and get the mass of it. Probably before it goes for a swim would be good, so it's not wet. And then you'll have the mass and you'll have the volume. You could then go into the density equation, obviously, and calculate the density by doing so. So in this case, the density of zinc, we have our mass of the zinc in this example, which you can get from the balance, as you can see there. We have our final minus initial reading here, which gives us our volume. Again, mass divided by volume. This is also really important here. A couple of things, which is here we're looking at 4 significant figures. Here we're subtracting, which means we're looking at decimal places, right? And we should go to 1 decimal place. And in that case, as you can see there, you get 9.5 milliliters. Although that has 1 decimal place, how many significant figures does it have? It has 2 significant figures, right? And that is why our answer will end up with 2 significant figures. So again, you want to be careful as you're doing it. And again, in this case with density, you sometimes will be doing subtraction and then doing some dividing or multiplying. So you do want to, again, keep track of those significant figures throughout your calculation. So those are 3 very common ways that you could get a volume. Just take a reading, take some length measurements, or again, do volume by displacement to figure out the volume of a solid. Any questions on that there? All right. So why don't you give this a go? What is the density in grams per milliliter of a 48-gram sample of a metal that when placed in a graduated cylinder that has 25 mils of water goes to 33 mils? See what you come up with here. Okay, so clearly in this case, we're dealing with density. So we should think about our density equation. Density is mass divided by volume. Oftentimes, a really good practice is to pull out the information and see what you have. It'll kind of maybe point you in the right direction if you're not sure. Obviously, here we have the mass given to us, which is 48 grams. We have an initial volume of 25 milliliters. Before we put the object in there, we have a final volume of 33 milliliters. So ultimately, we do have a volume, we do have a mass, so we can solve for obviously our density in this case. We do need to figure out our volume, and again, it is basically the difference there, right, between where it started and where it ended. So the volume of our object going to be our final volume minus our initial volume. So we're going to go 33 milliliters minus our 25 milliliters. And that's going to give us 8.0 milliliters. Here we do need 8.0 because we are subtracting and we are looking at decimal places. So that's 1 decimal place, 2 decimal places. We need the 8.0 for the correct answer there, not just 8, because 8.0 has, in this case now, 2 significant figures, which is going to play a pretty big role here in the last part of the calculation, which is our density is our mass, 48.0 grams, divided by our volume, 8 milliliters. And that's going to get us here, again, 48 divided by 8, going to give us, again, 6. Here we want to think about significant figures. So the end here we divided. That means the top number here has 3 significant figures, as we figured out a second ago. Bottom number has 2 significant figures. That means in this particular case, I actually need to add a 0, right, with a decimal point there to give me the proper number of significant figures. By the way, what happens with these units? Do they cancel? They do not. So the number stays with the grams part, and it's always 1 milliliter. You need both units still there when it's all said and done. Yeah. Any questions on that one there? So again, it's important to keep track of those sig figs as you go through it, and also units as well. So make sure you have units on everything. And in this case, they don't cancel, so you got to keep them around at the end there. Yeah. All right. Now, when we're given the density in a particular problem, you can definitely use the density as a conversion factor. And as I was talking about a second ago, when we're doing dimensional analysis, you could actually take kind of a dimensional analysis approach to the problem. And you don't even have to worry about the equation d equals m over v, because if you just do opposites, it will kind of take care of itself as you're doing it. So what do I mean by that? We'll just take the density we just calculated there, and we had 6 grams per milliliter. What that basically means is I have 6 grams in 1 milliliter, and I could use it as a conversion factor of 6 grams over a milliliter, or you could flip it around, put the milliliters up on top and the 6 grams on the bottom. And now let's just say, for example, I had, 325 milliliters, and I want to know, how many grams that would be. I could just take a dimensional analysis approach with this without even thinking about the formula, to be honest with you. I know I need to get rid of milliliters, so all I have to do is this. And just like we did earlier, to get rid of those milliliters need to go on top or bottom. They need to go on the bottom, which means I'm just going to use my density like this. And because I set it up with my dimensional analysis, I know that will cancel. But even more important in this case is I know what's on top will get multiplied, right? And what's on the bottom, which there's nothing really here, would get divided. So I just rearranged my density equation in this case to solve for mass, which would be volume times the density, without having to even rearrange it. And I already know the math correctly. I know I should be multiplying and not mess up and maybe divide when I shouldn't. So again, you could take a more dimensional analysis approach, especially if you're given the density, use it as a conversion factor. And like I said, you don't even have to worry about really rearranging the equation or anything like that. In this case, though, is that the right answer in terms of significant figures? I'm going to go with no. Yeah. So here we're multiplying. That has how many significant figures? 3. Do I need to look at the density significant figures? I do in this case, right? That's 2 significant figures. That means really this guy should end up here, which means we do need to round. So that is 2,000 grams. Is that the right sig figs? No, that's how many sig figs? I heard a lot of numbers there. I didn't hear 1, which I think was the only number that we actually need here. 1 is actually here, right? It was not 4 because there's no decimal, but if I did put a decimal at the end, now there's 4, right? And that's still not the right number. This is a case, as we talked about before, the only way to get the right number of sig figs, a little scientific notation action, right? 1, 2, and 3 would be the correct number of significant figures and the right meaning for it. So definitely I would recommend that if you come across density problem, you have the density, I would take a more dimensional analysis approach, and it's sometimes easier than worrying about, did I rearrange that correctly, or should I be multiplying or dividing? So again, that again is the benefit sometimes of doing things dimensional analysis way. A lot of times you could almost put some formulas to the side and not have to worry about memorizing them or rearranging them, and just kind of take that sort of approach. Any questions on that there? All right, so why don't you try one here? We are looking for the volume, and we have the mass given to us of 14.7 grams. Once again, you absolutely can just use the density equation. Just check things off. You got density, you are looking for the volume, and you have mass. So we could rearrange this and basically multiply the volume to each side, come back and divide by the density. And that'll essentially give you that the volume is equal to mass divided by density. You could also, again, take a more dimensional analysis approach, and now I'm going to have to worry about rearranging that equation. And I know that I have a density like this, which means I could flip it around if I needed to and use it in this sort of fashion. And in this case, frankly, I have grams I don't want. So even if you're not sure where you need to go, you probably know you don't want the grams anymore. So I need to get rid of that. So that's going to be this guy right there. And milliliters are going to go on top, opposite with the grams. Grams will cancel. At this point, I'm left with milliliters, which is a volume, and that's what I'm looking for. And again, by setting it up like this, it takes care of all the math for you. I again know up on top gets multiplied, on the bottom gets divided. So I know I should be dividing this number, as that's basically up on top, right? That number there. And that is essentially what we got here, right? Without rearranging the equation. And the dimensional analysis took care of all that for you. That gets you 14.7 divided by 1.32. Going to give us a lot of numbers there. 11.1363636 milliliters. Significant figure wise, we do need to look at our grams, which is 3 significant figures. We do need to look at our density number, which is this guy, which is 3 significant figures. I'm going to go with 3. Seems to be a winner there. 111.1 milliliters in this particular case. Yeah. Any questions on that? So again, hopefully you can kind of see that if you set it up like this, it can take care of not having to do something like that, yeah, that you might not want to do in certain cases. Or you can still do that if you're comfortable doing that, and you'll get the same answer. Obviously, if you just, obviously at this point, plugged and chugged into there, you'd get the same answer as well. Any questions on that there? All right. And last one here. John took 2 teaspoons of cough syrup for a cough. If the syrup has a Okay, so let's take a look at it again. If we pull out the information, we got a volume of 2 teaspoons. We have the density given to us of 1.2 grams per milliliter. Again, the number stays with the grams part. It's always 1 milliliter. And we are looking for really the mass or the grams in this case. So again, if we take our density sort of formula and we just check off, we have density, we have volume. We obviously want to solve for mass in this case. We would multiply the volume to the other side. That's volume times density. Once again, here though, we can take a dimensional analysis approach and see how we do. We are also given a conversion in here of 5 milliliters is 1 teaspoon. So we have sort of that equality given to us here. And that's important because, again, we can use our density as a conversion factor. We could flip this around and go a milliliter on top, 1.2 grams on the bottom. Much like we talked about previously, though, our volume and our density is in milliliters, but it's in teaspoons here, which means we do need to do that conversion. So we can use this equality here to get it in the right units so that we can then use the density as a conversion factor. So we will do that first. 2 teaspoons, again, opposites canceling. We're going to go 1 teaspoon on the bottom, 5 milliliters up on top. That's going to cancel, going to give us 10 milliliters here. Milliliters in this particular case as our volume. We now have really our volume in the correct units to use the density and a dimensional analysis approach. Here, this is 2 sig figs, by the way, right? And 2 sig figs. We do need to look at the 5 here, and we should end up with 2 significant figures. That's why I got rid of the 0 there at the end. Now that I have it in milliliters, I could just take a dimensional analysis approach and get rid of milliliters, which means opposite's going to do that for me, which is that density conversion basically right there, 1.2 grams per milliliter. Those are going to cancel. We're going to multiply in this case, and that's going to get us a 12, I believe, grams in this particular case. Any questions on that one? Again, significant figure-wise, this guy has 2 sig figs based off of obviously back here. This density we do need to look at has 3 significant figures. Once again, here we're multiplying, and that means we should end up with 12 in this particular case. Don't really need a decimal, put it in there for free. Yeah. Any questions on that? Our density. Obviously, you could just plug and chug into the density equation if you have the mass or the volume given to you. Any questions on that there? And as we talked about last time, we are not really skipping 3, but a recorded lecture for chapter 3 has been posted. Make sure that you do watch it. You are responsible for obviously the information in there, and that will hopefully help keep us on pace here with the holiday coming up on Monday, by the way, in case you're not sure. We do have a holiday on Monday. So we are then going to go to chapter 4. Which should be, I believe, the last chapter for the first exam, right? So again, make sure you are working on the homework for these chapters as we go through them. Don't wait to the last minute. Otherwise, you might be disappointed and you're not going to finish. Yeah, so make sure you are working through that. All right, so last time we finally finished up chapter 2, talking about conversions density. So in this chapter, we're going to talk about really the atom. We're going to talk about, not in great detail, but we'll kind of touch upon some of the experiments that led to sort of our understanding of the atom and the different parts of the atom. We will then talk about some sort of properties of the atom, things like mass number, atomic numbers, protons, electrons, neutrons. I believe we will also hit in this chapter the periodic table, I think, is in here. And we will finish up, I think, the chapter talking about mainly electrons and electron configuration. So there's a lot sort of in this chapter, and we should get started probably, I imagine. So let's talk a little bit about atoms and elements. And as we might have touched upon earlier on, atoms are really, as we'll see, sort of the basic representation of elements. And atoms, basically, as we will see, consist of protons, which are positively charged, electrons, which are negatively charged, and neutrons, which have no charge. Elements, as you can see from the periodic table behind me, you could think of it as really the sort of the basic building blocks of kind of everything in chemistry. Different combinations of elements will give you different compounds. You can think of it kind of like the alphabet, right? I think there's still 26 letters, give or take. And obviously different combinations of those letters will give you different words that have different meanings. Same idea in chemistry, sort of different combinations of even the same elements will give you some different compounds, which will have different properties and give you some different sort of substances along the way. So when we talk about elements, a couple of reminders, there are also molecules. And again, a molecule is a basic sort of definition of pretty much all you need for that is 2 or more atoms together. So if you have a molecule, that's basically the definition. And what I mean by that is essentially it could be 2 or more atoms of the same element. It could be 2 or more atoms of different elements. But in order for something to be a molecule, that's pretty much all you need. Is just need 2 or more atoms of something that's basically united together. And that's oftentimes confused with another word, which is a compound. And a compound is also 2 or more atoms together, but it is actually 2 or more atoms of different elements. And that's a really important distinction, is the different element part. In order for something to be a compound, you do need 2 or more atoms of those different elements that come together. So what I mean by that, again, sort of tie it to elements. We could have elements like K, which is potassium, which is just by itself. There are certain elements, for example, like hydrogen, that how they naturally come by themselves when they are uncombined with anybody is they come as H2, which basically means there are two hydrogens together, is what the little 2 means there. So basically, hydrogen, when it is all by itself and not attached to anything else, it comes basically as a 2-pack, if you will. And because that basically is 2 atoms together, that is what is sometimes referred to as being a diatomic molecule. And again, di meaning 2, atomic meaning atoms. So it basically is 2 atoms that come together. So in the case, for example, of hydrogen, it is an element. And it also is a molecule because it meets the definition of a molecule. It has 2 or more atoms together. Now, when we think about hydrogen H2, it is not a compound, and it's not a compound because the only atoms that are in hydrogen is hydrogen atoms. It's the same element. So it is not a compound. What is a compound? Something that we all see today, H2O, a little bit of water, right? So water here is a compound because basically water is a combination of hydrogen atoms and oxygen atoms together. So it meets the definition of a compound because it is 2 or more elements that are together. We have hydrogen and oxygen. Water is also a molecule because it meets that general definition of there's 2 or more atoms that are together. So water is a molecule, water is a compound. Water is not an element because it is not just one element by itself, right? So there's hydrogen and oxygen there, so it's not an element. So something like water is a compound. It is a molecule, but it is not an element. So again, that is the general definition. Our definition is really of molecules versus compounds. I personally like to think of molecules as just really like a basic definition of all you have to do to meet that sort of qualification of a molecule is you need 2 or more atoms together. And again, it doesn't matter if it's the same element or different. But for a compound, you have that extra sort of additional requirement for it to be a compound. You need at least 2 or more different elements involved for it to be a compound. Any questions on that there? Yeah. It doesn't matter how they're bonded. We'll talk about when we get to bonding in our chapter or so, but you can have, for example, this is a compound here, and this type of bonding that we see in water is what's known as covalent bonding. They're actually sharing electrons in this particular case. There's also, for example, ionic bonding, which happens when metals and nonmetals together, something like sodium chloride. And sodium chloride is considered also a compound because there's sodium and a chlorine together as well. So they can, and depending on what comes together, and we'll hit that in, I think, in the next chapter, actually. Yeah. Other questions? All right. So when we talk about elements, we do want to use the correct symbols. And typically, as you can see on the periodic table behind me, or have you seen probably on the periodic table, basically the symbols are really one of 2 sort of formats in terms of how they are written. If it is a 1-letter symbol, that 1 letter is always capitalized. So if you had, like I wrote earlier, potassium, which is K, you always capitalize the single letter by itself. Now, if you have a 2-letter symbol, which is really the other sort of symbol combination that you could get, we always capitalize the first letter, but not the second. So like we have here with aluminum, we would have a capital A and a lowercase l. So when you do write the symbols, it's really important to follow those rules. Now, if you're somebody that likes to capitalize everything that you write and only use capital letters, that's really problematic if you're writing formulas. So for example, if I write capital C and capital O versus capital C and lowercase o, the one on the left there, which is capital C, capital O, that is carbon monoxide, which is very different than the one on the right, which is the element cobalt. Yes. So you want to make sure that you do not write capital letters for all symbols. Even if you write everything capitalized, don't do it here because you'll probably get an X just like that there. You don't want that. So you might be actually writing something you're not meaning to do so by just capitalizing. So it's really important to make sure, again, if it is a two-letter symbol, only capitalize the first one and lowercase on the second letter. And if it's a one-letter symbol, you then would just make sure you capitalize that. Question on that there. Now, elements, as I mentioned, are pure substances. They are pretty much as far back as you could go. So, for example, we talked a little bit there about a compound. You could take a compound and you could do a chemical reaction with it, and you could break it back into its elements. So we had our water there. So you have your water. You could run an electrical current over the water there, do a little electrolysis, break it apart into hydrogen gas and oxygen gas. It's like a chemistry class. I'll do a little balancing there. But you basically can take something like a compound and through some type of chemical means, like a chemical reaction, you could break it back into its elements. We also see here as well, in addition to hydrogen, oxygen also comes in its natural state as a diatomic molecule. There's actually 7 elements that come naturally as twos. Those are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. So those 7, again, the way that they come, when they are uncombined with anybody else, they come as twos. So, and they also come as twos, not that it's necessarily that important in terms of their formula, but they come as twos bondedly different. So like hydrogen comes as, for example, a single bond. Oxygen actually ends up as a double bond, and nitrogen ends up as a triple bond. And when we talk about bonding, we'll talk about why that all ends up that way. But they actually come differently bonded as well. But the main thing is they always come as twos. So if you ever see anything in sort of words and you need to eventually turn it into like a formula or something like that, and they say hydrogen gas, that's H2. They say molecular hydrogen, molecular oxygen, that is H2O2. Again, that's how they naturally come. That's pretty much here on the periodic table. We got our hydrogen, our nitrogen, oxygen, and this down this group basically there. So kind of from here over and down the group on the periodic table, that's where you find all your twos. By the way, pretty much everybody else on the periodic table comes as ones, pretty much. So they all come as ones, which are known as being monoatomic. They come as one atom basically together. While we're speaking of that, and we'll talk about it in a second as well, I'm sure, but a little reminder, just in case you don't know, we'll eventually start talking about things that have charges. But if you have any element off the periodic table by itself, once again, uncombined, not attached to anybody else, they don't have charges. So they're all neutral. Things, as we'll talk about again in the next chapter, only really gain charges when they start hooking up, mainly metals and nonmetals. When they come together, that's when they really start to form charges. But if you had, for example, a piece of copper metal, it doesn't have a charge. It's neutral, basically. So anything that basically you pull from the periodic table is essentially neutral, unless obviously it reacts with something else that could give it a charge. Any questions on that there? Now, as I mentioned, you could break compounds into elements, but that again is as far as you could go. So you can't break it apart any further than elements. And again, that's kind of your basic units there. So here are some of the symbols for some elements. And again, you can see the combination there of either a one-letter symbol which is capitalized, or a two-letter symbol where the first one's capitalized letter and the second one is not. Really, the names and things for these elements come from a wide variety of sources. Kind of planets, as you can see, they also come from scientists' names. They come from places where they came about, philosophers, all these type of things, right? It's how we get, elements like Californium. I'm assuming it comes from California, right? Berkeleum, maybe up at Berkeley. You know, we have Nobelium, Einsteinium for some, scientists and stuff like that. So they do come from a wide variety of sources, and that's maybe why sometimes some symbols that you see, you maybe are wondering, like, where's that come from? Like, for example, lead. Lead is PB, nothing with an L, lead, right? So lead is actually PB. Um, for example, iron as well. Iron is Fe, right? And obviously that doesn't perhaps make sense, but it is from the root of sort of where they come from. What should you know in terms of symbols? Well, you should know, I was going to say all of them, but eventually maybe not. I'll be honest with you, when you look at the periodic table, we deal a lot with kind of to the left. We do deal with to the right. And I would say kind of up here and over and down. We don't do too much with the bottoms here, and not too much in like this area here, but definitely left, right, kind of top, and then as you go to the right, kind of angling down, we kind of hit the. I would, if you haven't done so already, I would start really taking a look at the names that go with the symbols. Not necessarily that you need it extremely a lot in this particular chapter per se, but the next one we're going to get into will involve talking about naming things. So there's obviously rules to how you name everything. And if you're still trying to figure out what symbol is what, it's just going to make it a lot harder. So I would, from now, until we kind of get into that next chapter, I definitely would try to get some handle on, some of the symbols and their names that go with it. It's just going to make kind of when we get to the naming part, hopefully a little bit easier. You will obviously be given a periodic table that does not have the names. Yeah, so we'll have the symbols. So again, you need to kind of know, what the symbol and the name kind of goes with. So again, carbon, which I did good. I usually say copper and copper, carbon. So carbon C there, sulfur S, nitrogen N, hydrogen is obviously H. We do a lot here over here with our fluorine, F, chlorine, bromine, iodine, sulfur, phosphorus, aluminum, silicone. So again, like I said, a lot of these over here, we do touch upon. And in this area as well, there's our lead, which is PB. SN is tin. SB is antimony. BI is bismuth. So those we pop up. And then over here as well, gold, AU, right? Silver, AG. Mercury also, HG, pops up a lot. And like I said, zinc, ZN, copper, CU, cobalt, as we talked about. So again, getting some familiarity with those. My favorite element, number 34, selenium, right? Never know where that one pops up. So make sure, you start getting that sort of understanding. So again, here are some of the symbols, and it will definitely make the kind of naming part that we get into a lot easier if you have some recognition of it. And again, as we were talking about iron and lead, those are, again, really where those symbols come from. Those sort of common names, Latin names that are used sometimes to for the symbol, also for copper as well. That is, again, sort of where it comes from. All right, so here's a few other ones there. All right, so let's take a look at some of these, just may help. So we want the symbol for each of these. So iodine is I, yeah. Iron is Fe, magnesium, Mg, zinc, Zn, lithium, Li, yeah. So again, one letter capitalized, two letters. First one capitalized, second one not. Go. All right, so try some of these names. So P is phosphorus, yeah. So that's phosphorus. AR is argon. That's a noble gas right over there. Mn is manganese, not to be confused with magnesium, right, which is Mg. So Mn is manganese, right about there, number 25. Be is beryllium, and K is potassium. So again, like I said, um, you definitely probably sooner rather than later want to again get some familiarity with the symbols and the names that go with them. Again, it's just going to make kind of everything a little bit easier as we get into sort of, I won't say real naming, but real naming. Yeah, when we get into how you name everything else, basically. Any questions on that there? Okay. So let's talk a little bit about the atom here and the structured atom. We're going to kind of touch upon some ideas and concepts that really helped us understand, what the atom sort of looks like. As I mentioned previously, the atom basically is made up of three subatomic particles, which are protons, electrons, and neutrons. And really, and neutrons have no charge. So really, a lot of the discovery of the atom came about after a few theories about what atoms were and sort of what they were made out of. And the idea of the atom, as we talked about, is again really your basic representation of any element that you have. So any element that you may have, basically the representation of that element is basically an atom. And a long time ago, uh, a guy by the name of Dalton, John Dalton, he came up with a theory on sort of what atoms were. And these are some of the parts of his atomic theory. And in the case of a theory, as we talked about, I think there in chapter 1, a reminder that a theory is something that maybe is not 100% correct in all aspects of it. It may be thought to be correct, and then maybe further experimentation down the road might disprove some of it, may prove some of it correct and some of it incorrect. And that happened actually with Dalton's atomic theory. So he basically said that all matter is made up of these tiny particles, which are called atoms. And one of the ideas from Dalton, and even really before Dalton, was sort of this idea that atoms are sort of indestructible. And you can't really do too much to them. And the idea of that is one of the ideas that are sort of not necessarily correct. And with the sort of idea of nuclear reactions, you can sort of change one element into something else by changing what's in the nucleus and stuff like that. So that part of it is not so correct. It is correct, the idea that they're made up of these tiny atoms. That's correct, part of it. He said that all atoms of a given element are identical to one another, and they are different than atoms of different elements. So, also part of that is correct, and part of it is not so correct. So, the part that's not so correct is all atoms of a given element are identical to each other. The existence of what are known as isotopes basically disproves that idea. And the idea of what isotopes are, they are different. Sorry, I say it right. They are the same element, but they have different masses. So even though they're the same element, they actually have different masses, which means they clearly cannot be identical to each other because they have different masses. So that part of Dalton's atomic theory is also sort of incorrect. The idea that every atom of the same element are identical to each other. Now, the second part of that is okay. The part where it says that an atom of one element is different than an atom of another. So if you had a copper atom versus an iron atom, there are differences in those two. They are not identical to each other. So that part's all good. He also said that atoms of two or more different elements combine to form compounds. And that is correct. A particular compound is always made up of the same kind of atoms and the same number of each of those atoms. So an example of that is water, right? No matter where you get your water, it ultimately is two hydrogens together along with an oxygen, pretty much, right? May cost you more depending on how it's bottled, but it's pretty much H2O, right? The core of it, what it is. And no matter where you go, if you have water, because hydrogen is essentially 2 grams or 1 gram, and there's 2 of them, so 2 grams of hydrogen for every 16 grams of oxygen. No matter where you find your water, you will always have a ratio of, for every 1 gram of hydrogen, you'll have 8 grams of oxygen present because of the mass ratio. The other important sort of idea of Dalton was the idea that a chemical reaction only involves the really recombination of elements. So in a chemical reaction, we do not lose any elements. We do not make new elements. Whatever we start with and whatever we finish with are the same elements. They're just combined differently. So what that means, for example, is if we have an arrow, and this is our reactants, which is our starting materials, say in a chemical reaction. And let's just say we had 6 carbons we started with in a variety of things. So there's a total of 6 carbons on the left-hand side of the arrow. When we're done and we make our products, which is what is made as a result of a chemical reaction, you will still have those same 6 carbons on the left-hand side of the arrow and the right-hand side of the arrow. They will be in different compounds probably, or different substances, but you will still have basically the same amount of carbons on the left-hand side of the arrow and the right-hand side of my example. That is what is sometimes referred to as the law of conservation of mass. We don't create nor destroy anything along the way. That's also who you could thank for when you have a chemical equation, why you have to balance it. So you have the same number of elements on each side of the arrow. So in a normal chemical reaction, as we'll talk about, pretty much it only deals with bonds making and breaking, and that is actually only electrons are involved in that. So only electrons are involved in that process. And that is different though than nuclear reactions. In a nuclear reaction, all you do is play with what's in the nucleus, and you change things all day with doing that. And that's why in nuclear reactions, you don't have that conservation of elements. What you start with and what you end with are very different things, very different elements, because you're actually changing what's happening in the nucleus. But what we deal with in here, since we don't do the nuclear chemistry chapter anymore, we won't deal with it at all. But we only deal with chemical reactions here. So we have that conservation of elements in a chemical reaction. However many, one element you start with on the left-hand side of the arrow, you should end with the exact same amount on the other side. And the idea of the conservation of mass is a simple one as well. Since carbon is 12 grams and you have 6 of them, you should also have at the other side of the arrow 6 times 12 grams conservation of mass of your elements from your reactant side to your product side. You'll have the exact same mass of each of those guys present. Now, as I mentioned before, atoms were believed to be very small, and they are. But even though they are really small things, they are made up of even smaller particles, and those are our subatomic particles, and that's our protons, electrons, and neutrons. So we have atoms, which are the basic representation of elements, really small things, and they're made up of even smaller particles, those 3 types of particles which have those types of charges. So along came this idea of trying to explore the atom and understanding where these sort of particles maybe are. And one of the really important sort of concepts in chemistry, and was also really important in sort of looking at the atom and exploring the atom, is the idea of opposites attract. And opposites attract, as was sometimes referred to as electrostatic attraction. Basically, opposites attract, right? Much like in life, right? If you have two positive people, that's a lot of positivity to be around, right? And if you have two negative people, that's a lot of negativity to be around. They say you want to try to find something that balances you out. So slightly positive, slightly negative, nice mix right about there. So same thing happens in chemistry. If you have something that has a positive charge and a negative charge, they will be attracted to one another. So positive things and negative things are attracted to one another. That is what is referred to as electrostatic attraction. If you have negative and negative things near each other, they definitely do not want to be near each other. They will repel each other, like we see here. They will try to get away as far as possible. Same thing with positive and positive. You have two positive things near each other, they also are going to try to get away as far as possible. But you throw a positive and negative thing together, we're going to kind of stick together. It's going to stick, and they will be attracted to each other. That is probably in chemistry one of the strongest attractive forces you could have, like an electrostatic attraction, positive and negative coming together. Sodium chloride, which is NaCl, is held together by that type of attraction. You ever heat up salt, you could heat it all day. It will never come apart and make gas. They will stay together. It will just start melting before it tries to go into the gas phase. So it's an extremely, extremely strong attractive force, that sort of opposite attraction that occurs. So how is that helpful when they were sort of looking at the atom and trying to sort of explore the atom? Well, what a lot of experiments used when they were doing that was radioactive particles, and three types of radioactive particles that were used in a number of experiments. One is an alpha particle, which is that's the symbol. An alpha particle is a positively charged radioactive particle. It is essentially that guy right there. It's essentially helium. Is basically what it is. They also use beta particles with that symbol there. Beta particles are negatively charged radioactive particles. And they also use gamma rays. And gamma rays have actually no charge. And they are really pure energy. They are extremely strong in energy, as we might see a little later on in this chapter. It is a very strong energy that comes off. If you ever work with anything that is a gamma emitter, you need a lot of protection to protect yourself, and you shouldn't be around it all that long. So a lot of experiments really took advantage of these charges, and why having things that have charges is really important is you could also use something like an electrical field. If you had an electrical field, there's a positive and negative sort of side to that field. And if you were to, for example, shoot a particle through an electrical field and you saw the particle kind of bend towards the positive side of the electrical field, that would probably tell you the particle has what type of charge? Negative, right? Opposites attract. If you shot a particle through an electrical field and it kind of bent towards the negative side, then you know probably that guy is positive. And if you shot it and just kind of sailed straight through, ignore my non-straight line there, but it went straight through without moving one way or the other, I probably had no charge as it was unaffected by an electrical field. A magnetic field works the same way. There's a North Pole, South Pole, does kind of the same deal, kind of bend one way or the other, depending on the charge. So a lot of experiments when they were sort of exploring the atom used sort of this idea and this sort of discoveries to their advantage. And probably the earliest sort of exploration of the atom was one done by J.J. Thomson. He used what is referred to as a CRT, which is known as a cathode ray tube. And a cathode ray tube you may be familiar with. Used to be like old TVs, yes. Maybe some family members or you have some. They used to be on the floor. Used to call the TV repairman. They opened up the back of the TV and actually repaired like the picture tube. None of the TVs we have these days. Nothing. None of these guys, no. But those all had picture tubes. They were CRT tubes in there. Even computer monitors used to be CRT monitors. Those are the ones that had like the big back on them. Maybe you've seen them in a picture or something like that. Again, not this. That is not. That's why years ago, parents used to say, don't sit in front of the TV. You're getting shot by all those rays. Because it had an actual picture tube in there that was doing those things. So the CRT tube is basically this idea. It is a tube, and it actually has charged plates on one side versus the other. So it has a positive side and a negative side. And it actually was a stream of negatively charged particles like an electron, which would actually start moving this way, away from the negative side towards the positive side. And on this side, they would coat it in the screen, and you could actually see where it's actually hitting and stuff like that. So Thomson did a lot of experiments with the CRT. A guy that followed them up was a guy named Milligan. Milligan did what is known as the oil drop experiment. And basically, that experiment also takes advantage of sort of an electrical field and charges. He had a chamber where there was an electrical field. And what he did, much like the title implies, he shot oil into it and basically heated it up, atomized it. And what he would have was like a little opening where a drop of oil would go through. And as that oil was dropping, it would gain a charge through friction. And what he was able to actually do was like dial in the electrical field where essentially he was able to suspend the oil droplet. Basically, kind of dial it in. It wouldn't fall, wouldn't go up, wouldn't go down. And those two experiments were really important in terms of understanding the electron. And what we were able to understand in terms of the electron was Thomson figured out the charge to mass of an electron. And Milligan actually figured out what the charge was on an electron. And the importance of really those two experiments was if one figured out the charge to mass and one figured out the charge, we could do a little dimensional analysis there. We got the charge divided by the charge to mass of an electron. Charges cancel, leaves us the mass of an electron. And so from those experiments, they were able to figure out the mass of an electron. And it roughly is 9.09 times 10 to the minus 28 grams. Some books now like to round up to 9.11, but we'll go with 9.09. Is that a large number or small number? It's a really small number, right? It's like 28 places to the left and add a bunch of zeros, right? So it's a really, really small sort of number. So a really good understanding of the atom was really started, especially electrons, through these two really important experiments. And they were able to figure out really the mass of an electron. And what happened was after these sort of experiments, the idea was this. They knew obviously that the atom contained electrons, which are negatively charged, but they also knew that the atom was neutral. So they knew at this point that the atom had electrons, but it was neutral, which means in order for it to be neutral and it has negatively charged electrons, there has to be some type of positive component to the atom to balance out the negatively charged electrons. So what this led to was really a early model of the atom, which was done by Thomson, and it was referred to as the plum pudding model of the atom. Plum pudding is like a kind of rice dessert there with raisins and pudding, and the raisins are kind of in the pudding. And the idea of what they said was, all right, we know it's neutral. It's got to have some positive charge somewhere. So as the picture you see down there shows, it basically what they thought was all the positive charge was pretty much just diffused over the entire sphere. So you have the sphere, a positive charge spread out all over it. And embedded inside this sphere, like the raisins in the pudding, are the electrons. So you got all these electrons that are embedded inside. And they also felt at this point that most of the mass of the atom was the electrons. So this was sort of an accepted theory of the atom at this point, based off of these experiments and what has happened before, that we have this positive charge that's spread out all over the place. And we have these electrons embedded in the pudding there of positive charge, and most of the mass of the atom is made up of these electrons. And as we talked about in terms of models or theories, they're only as good until they get disproven, right? And that is actually the case here. Along came really the next big experiment that really helped us understand truly what the atom looked like, or is basically made out of. And this was done by a guy named Rutherford. And Rutherford did the gold foil experiment. And basically, what it sounds like is he took alpha particles. So remember, these alpha particles are those positively charged radioactive particles. And he basically shot them at pieces of gold foil and other atoms. Now, the idea of what they thought was going to happen based on the plum pudding model to what they actually saw happen was very, very different. So, if we think about sort of the model of the atom that they were thinking about, which was we have all this positive charge spread out, we have these electrons that are embedded inside, and we're going to basically shoot these alpha particles, which are positively charged particles, at a big pudding of positive charge, right? So, what they thought would happen would be kind of this. We're obviously shooting something positive at something that's ultimately positive, which means they should repel each other, except that the positive charge is spread out all over, right? So it's not really thick, if you will, right? It's kind of a thin positive layer, if you want to think about it. So kind of like my paper here, if this was the atom, nice thin positive charge all spread out. If I were to hold this paper on one side and really held it tight on the other side, and I shot like a pen or something at it, it's moving really fast, right? It's heavy, and I shot at it. It's probably going to be able to pop through the paper, right? But as it does, it's probably going to deflect a little, right? As it's able to go through there. And that's what they really thought was going to happen here. Because these alpha particles are heavy, they're moving really fast. They felt that when they shot these things, it should kind of go through, but there would be some deflection as it went through it. Because again, you got positive and positive, but again, it's moving really fast. So kind of just a little bit of resistance as it kind of pops through the spread out positive charge. And they were very, very surprised when they actually did the experiment. When they did the experiment, this is pretty much what they saw. Most of the particles just sailed right through, no problem. But what they also saw was every so often, they would see an alpha particle bounce off at really large angles and even like head back to where they came from. I imagine if you were standing there, not so great, but bouncing off these really, really large angles. So that told them a couple of things that was really important about the atom. The first thing that it told them was perhaps this plum pudding model not so good, right? Because we clearly didn't see what we expected, right? If we had this nice diffuse positive charge, we should see those guys pop through no problem. Nobody should be bouncing off at these really large angles. They should pop through. It's a little bit of deflection as they go through it. They shouldn't be coming back to us. They shouldn't be bouncing off at super large angles. And that's what you see here. Again, most of them went straight through, but every so often they would see these guys kind of bounce off at really sort of large angles. So they wanted to think about sort of what they just witnessed when they did this experiment. So let's think about it. If I were to throw my pen that way with nothing in front of me, my pen is just going to go straight, basically, right? And that's what they figured out. They figured it out that pretty much all those alpha particles that just went straight through, no problem, pretty much hit nothing. Nothing got in its way, right? So had no problem going straight through empty space. But now, what would make an alpha particle jump out at a super large angle? It had to hit something that was very, what type of charge? Positive charge, right? Alpha particles are positive. Has to hit something that's really, really positive. Not just positive, but super densely positive to make that really fast moving alpha particle bounce off at that super large angle, right? Because that thing is heavy and it's moving fast. So it had to hit something just as densely positive to make it ricochet basically off at that big angle. So they said, well, we have to really throw out the plum pudding model and go, clearly the atom is mostly empty space, which accounts for why all those things went through no problem. And maybe our positive charge is not spread out all over the place, but maybe if I took my paper in my example and I folded it right, all my positive charge down, which clearly you could just fold your positive charge if you need, right? You keep folding, where they say 7 times you can't fold anymore or something like that, right? 7 folds and you can't do anymore. Now, if all my positive charge was all concentrated in this area, right, and I take my pin and I throw it, it most likely is going to bounce back at me, right? Because it's not going to be able to pop through. It's just too much positive charge in there. And that's basically what they discovered from their experiment. They decided that the plum pudding model was really not correct. So they had to come up with this sort of new model of the atom. And basically what they said was the atom is mostly empty space. So Rutherford basically said mostly empty space. It also must contain a pretty dense positive core that they call the nucleus. So it has a dense positive core known as a nucleus. And in that nucleus, it was later found to contain protons, which are positively charged. And later on, like in 1930s, 1932, for example, it was found to also contain neutrons, which have no charge. And the other difference between sort of the plum pudding model and really this model of the atom was, instead of the electrons being most of the mass of the atom, most of the mass of the atom was the nucleus. So most of the mass of the atom is the nucleus, and we'll talk about in a second why that is as well. So really their model of the atom is we have kind of this nucleus, which is really positively charged, again, contains protons, later, not at this time, contains neutrons. We have our nucleus. And traveling in that empty space is where we find our electrons. So that empty space is sometimes referred to, sometimes as the electron cloud. And we have electrons traveling out from the nucleus at some point. By the way, as we'll talk about, electrons do not travel in pretty circles. They travel randomly about the nucleus. They don't travel in pretty little circles and orbits and stuff like that. They travel really randomly about the nucleus. By the way, should there be any attraction between the electron, which is negatively charged, and the nucleus, which is ultimately positively charged? Is there attraction there? There absolutely is. It's why your electrons just don't leave, right? They're kind of stuck to it like a rope, basically, right? Some electrons are strongly attracted to it. Some are still attracted to it, but not as strongly. And the distance at which these electrons are traveling from the nucleus accounts for whether or not, for example, they're involved in bonding or not involved in bonding. There are certain electrons that are involved in bonding, which are the ones that are furthest away from the nucleus. Because they're further away from the nucleus, they're still held, but they're not held as tightly as those electrons that are much closer to the nucleus. They're like feeling the full brunt of that positive charge, and they're held a lot tighter. So that's accounts for, as we'll talk about, why only certain types of electrons, for example, are involved in bonding and others are not. Any questions on that there? All right. So there we go. We got our nucleus, protons, electrons on the outside, neutrons in the middle, and protons in the nucleus. In terms of mass, we talked about the electron. And again, it was like 9.09 times 10 to the minus 28 grams. Just to kind of give you a reference, our protons were found to be in the ballpark of 1.673 times 10 to the minus 24 grams. And our neutrons were found to be 1.675 times 10 to the minus 24 grams. Actually, it is the neutron out of all three of those subatomic particles, which is actually the heaviest. It's just slightly beating out the proton. And neutron very close to each other, but the neutron is actually the heaviest, followed by the proton in terms of mass. The electron is about 1,800 times lighter than any proton or neutron there is. So the electron is much, much lighter than those other two particles. That also reinforces the idea of Rutherford, which is most of the mass of the atom is made up of the nucleus. And that is because in the nucleus, you have both of these guys there. And each one individually is about 1,800 or so times heavier than any little electron that's flying around. So that's what makes sense that most of the mass of the atom is actually made up of the nucleus. Any questions on that there? You could think of the atom as, since we just saw the Super Bowl, the Superdome. Yeah, like the Superdome there. And the nucleus is like a marble on the 50-yard line. Yeah, so super small volume, the nucleus. Super large mass, though. Yeah, it's the most of the mass of the atom containing a very small volume of the atom. Most of it is empty space as things are flying around. Any questions on that there? Okay. All right, so which of the following is found in these descriptions? The one we find outside the nucleus is? It is the electron, right? The one that has a positive charge is proton, and the one that no charge is? Right. And again, neutrons, like I said, actually were only discovered in 1932, really, basically. A guy by the name of Chadwick discovered them. He did a lot of work, and what he saw actually happen was a lot of radioactivity coming off, very similar to gamma rays that have no charge. And again, that's, if you think about that alpha particle, kind of similar to a proton in terms of charge, beta kind of like an electron, which is essentially what a beta particle is, and then a gamma ray is very similar to a neutron, no charge. So again, that's why those sort of radioactive particles were really important in discovery of the atom. In each of the following, true or false, the mass of an electron is greater than the proton. It is false. Again, it's about 1,800 times less massive. Protons have positive charge, electrons have negative charge. That is true. The nucleus of the atom contains only protons and neutrons. That is true in that case, right? Again, electrons are not in the nucleus. They are outside of it flying around. Any questions on that there? All right. So there again is the picture, like I said before. I guess it kind of shows up there. This kind of bluish area here, there's kind of like a darker area here, and then it kind of gets lighter as you get away from the nucleus. That again is what is sometimes referred to as electron cloud. And as I mentioned, because electrons really don't travel in these fixed orbits or anything like that, they travel in what are known as orbitals, and they are basically probability maps. And that's what this sort of picture is. Sometimes you'll see it as like a reddish type of color. And basically, when you look at it, the darker areas are a higher probability of finding an electron. Kind of the lighter areas of the color is a less of a probability of finding an electron. So you can see, if you kind of see it up there, but the darkest kind of blue is right around the nucleus, which makes sense. Again, the nucleus being positively charged. So there is a pretty good probability that you should be able to find an electron near it, since it is negatively charged. As you again fan out away from the nucleus at some distance, gets a lot lighter blue in that area. It means that there's still a possibility of finding an electron out there, but obviously less of a probability than if you're really next to the nucleus. For sure, you're going to probably come across one. That still means I don't know how the electron got there. I don't know where it's at actually, or how it's moving. That is what is known as the Heisenberg uncertainty principle. A particle like an electron, the more you know how it's moving, the less you know about its position, and vice versa. The more you know about its position, the less you know how it's moving. So when we talk about electrons moving around, that's why we don't kind of follow the Bohr model of the atom, which is that orbital model where everything goes around in a pretty little circle and stuff like that. It doesn't actually travel that way. But the best we could say is, I think in this area, there's a good chance of finding an electron, but I'm not really sure where it is or how it got here, if it does get here. But there's a good chance at some point you might run across an electron. rather than like the sort of Bohr model, which is that orbital model where it's in this orbit, it's going around in circles. You kind of put your finger there, eventually it'll come back around, right, and hit it. And again, they really don't travel in that sort of fashion. All right, any questions about the atom and how we got to it? So you should know a little bit about, again, those kind of experiments to the level which we talked about it. You should probably know the early model of the atom, which is the Plum Pudding model, and Rutherford's experiment and what came out of it, which is really sort of the modern version of the atom. Protons, electrons, neutrons are, and what sort of came out of it. Okay, we're going to continue on here. Now that we've talked about how the atom sort of came about, if you will, I guess, or really the discovery of sort of what the atom looks like, we're going to talk about some properties of the atom, including atomic number, mass